Very good. So now I want to share my screen, and we'll work through at least a little bit of the course material to date, on the basis that there aren't any logistic questions going waiting for me. Okay. All right. Can everybody see that? Now I really do need somebody to answer.
Yep.
Okay. So having given you an outline of what the course is going to be about, just in general, let me tell you a little bit about what the course is going to be about today. So we're going to start off by talking about complex valued functions and their derivatives. I want to go through this course kind of in the way you would have learned about calculus in first year. Right? So this course is really about calculus on the complex plane, and I want to talk about calculus in the complex plane the same way, following the same strategy that you learned in first year, which is to start off with talking about functions on the complex plane. So these are the things that you're going to be working with. The functions on the complex plane are the things you're going to be differentiating, are the things you're going to be integrating, right? And then we're going to essentially build towards differentiation. And you would have learned that in first year already that two key concepts with differentiation are the idea of limits and the idea of the continuity of functions. In first year, when you learned about derivatives and continuity and differentiability, you were essentially working on a line, on the real line. And when you work on the real line, essentially what's going on is that you have 2 degrees of freedom. You're allowed to move to the left and you're allowed to move to the right. So when you talk about a function and points and nearby points, you're talking about nearby points that are to the left or to the right. The complex plane is, as the word indicates, a plane, which means that there's more than just left or right. There's, in fact, an infinite number of directions that you could talk about on the complex plane. So in particular, the idea of limits and continuity and differentiability become a little bit more tricky on the complex plane. And this is something that you ought to keep in mind as we go along. What we're going to see is that there's one condition which can be stated in many, many different ways. And this is the condition of analyticity of a complex valued function. And analyticity of the complex valued function really tells you about whether this function is differentiable or not. And it, in fact, tells you how to differentiate it. So having established then limits and continuity, we will then move on to how to actually talk about derivatives on the complex plane. And again, I'm going to be working in the simplest way possible, which is first principles. So we're going to be talking about derivatives from the perspective of the Newton quotient and its limit. All right. So let's start then. A complex function, let's say f of z, is a mapping between 2 complex planes. Sorry. It's a mapping between 2 complex planes, which I'm going to call C sub z and C sub w. That just means that I'm going to talk about coordinates on the one complex plane using the complex variable z, and coordinates on the other complex plane using the complex variable w. And complex functions are a map, same way that they were a map in your first year calculus course, between the z plane and the w plane. So one way of saying this is that f takes z in the complex z plane to w in the complex w plane. So I'll write down very often that f of z is w, and that's what I'll mean. Okay? Well, z and w have real and imaginary parts. So we can, in fact, expand this function, this complex valued function, f of z, in its real and imaginary parts. So, for example, if I write down z as having real and imaginary parts x and y, so z can be written as x plus iy, then this function f here is really a function of 2 variables, 2 real variables, x and y. So then sometimes I might write f of xy. And if I write w, then as u plus iv, say, then what I'm saying is that this f of z, which is w from what we wrote down here, is just u plus iv, the real and imaginary parts of the complex variable w. But each of u and v is also a function of z and therefore a function of x and y. So if you really want to think just in terms of real variables, then all we're doing when we talk about variables on the complex plane, complex valued functions, etc., is study things on a two-dimensional plane, right? The mapping goes from the xy plane to the uv plane. Is that clear? A thumbs up on the reactions will suffice. Excellent. Okay, great. So let's do an example. The example that I want to start off with is a very simple one. It's a quadratic function. So suppose w, which again is f of z, is z squared. In other words, this function f of z takes some z in the complex z plane and just squares it, multiplies it by itself. Okay. The question we would like to ask is, how does this function act not on a point, but on, let's say, some geometrical object like a line in the xy plane? Okay, so this is the question I would like you to keep in mind. How does f of z equal to z squared act on a line in the xy plane? Right. So this necessarily involves putting things in a slightly simpler form. So let's, in a way that we can exploit the fact that we know what a line looks like on a real xy plane. So we know that z is x plus iy and w is z squared. So w is x plus iy squared. I know how to square complex numbers. You know how to square complex numbers. It's the real part squared minus the imaginary part squared plus 2 times the real part times the imaginary part. It's binomial, right? X squared minus y squared plus 2ixy. And now if I group things in involving I and things decidedly not involving I, then I can write down what, then I can identify what the real and imaginary parts are. So u here is identified as x minus iy, and v, the imaginary part of f of z, is 2xy. Is that clear? Good. Okay. So then my question was, what does this do to a line on the complex plane? Well, a line on the complex plane is the same thing as a line on the real xy plane. And I know that a line, let's say passing through the origin, is given by y equals mx, where m here is the slope of the line. Okay, so you learned this in school already. I can characterize a line passing through the origin by its slope. I'll call that slope m, which is the ratio of y to x. So what happens to this line under this map that goes z squared? F of z is z squared. Well, we know that u is x squared minus y squared, but y, we've just decided on this line, everywhere on the line, y is equal to mx. And so this is just x squared minus m squared x squared, which is 1 minus m squared times x squared if I pull out a common factor. And v, which was 2xy, is just 2x times mx. So it's 2mx squared. Okay. So just forgetting about this piece here. Don't worry about this for the moment. Let's we'll get to that just now. So we know that u is 1 minus m squared times x squared, and we know that v is 2m times x squared. So one thing I can do, if I want to know what happens to this line under this complex mapping, is eliminate this x out of the story, right? X is something that belongs in the complex z plane, in the xy plane, right? We really want to know what's going on in the uv plane. So if I eliminate x out of this equation, so I solve for x from, let's say, here, I solve for x from here, and I substitute it into here, then I will find that v is just proportional to u again. And the proportionality constant is 2m over 1 minus m squared, m being the slope of the original line that we started off with. In other words, what happens under this map, which is a quadratic map, right? It takes z and it squares it to give you z squared. What happens under this map is that all lines get mapped to lines. This is a line. V is something times u. Looks like y is something times x. The slope of this line, on the other hand, is related to the slope of this line. It's not the same slope, right? This slope is 2m over 1 minus m squared. Okay, that slope was just m. So what we learn then is that lines get mapped to lines under y equal to, w equals z squared. Is everybody with me?
Except for when m is 1, right? Then we have
correct. Except when m is 1, this thing blows up, right? So this will come a little later when we learn about singularities and where these singularities lie and why this thing blows up. Okay. What I would like you to show as, okay, so I need to make one more explanation here. My notes tend to be coming in 3 colors. This is on Zoom on my iPad, but it's the same in class as well. The white chalk text is the main text that we're talking about. Yellow is typically things that I'm commenting on. As you can see here, for example, I'm commenting on various things. Blue constitutes examples that I'm doing. So if you see any chalk that's in blue, then that's an example. And then red are exercises. So the red exercises fall into 2 categories. They're quick calculations, things that shouldn't take you long at all. If you're sitting on the jammy shuttle and you're bored, pull this out and try and show it. It shouldn't take you longer than your average jammy shuttle trip to, well, okay, maybe in traffic, you can do one of the challenge problems. But these are supposed to be quick 5-10 minute problems that you can do quickly without much effort. They usually lead on to other things. So I leave these quick calculations littered all over the place for you to do. And when you do them, they usually kind of follow on to other things. Things that you can get anyway without doing them, but they're very important for you to do so you understand where we're going. So keep that in mind. Then there's other exercises which are actual exercises. They're longer, they're more detailed. They're also kind of important to the flow of the problem. All of these red exercises that I throw around in the class, please give them your best shot at doing. You will learn a lot from it. They're not the type of questions that will typically come out in tests and exams, and yeah, this is me being honest with you. But they are the types of questions that you're really going to learn things from. Okay, so please give them a good shot, even if you don't get them completely right. At least give them a try. So as an example of such a quick calculation, what I would like you to show is that if I have some line on the XY plane, whose angle with the positive x-axis, theta here, is from your elementary high school trigonometry, is just the arctan of the slope of the line. So theta is just arctan of m. What I would like you to show is that under the mapping z to z squared, this line goes to another line, but the angle that line makes with the positive u-axis is twice the original angle. So theta goes to 2 theta. Okay. This is also set out in the notes, so you can take a look there as well. Well, what should be clear here from this mapping in this quick calculation is that under the map w equals z squared, half of the complex plane gets mapped to the full complex plane. So how do we see that? Well, one way to see it is if you think about that blue line, right? So suppose I take a half line that starts at the origin, so a ray, and extends all the way out to infinity. And then in the xy plane, I let theta go from 0 to pi. So that blue ray traces out the upper half plane. So what's happening as the blue ray traces out the upper half plane in the XY plane? Well, if z squared maps theta to 2 theta, then as theta goes from 0 to pi, the green angle is going from 0 to 2 pi. So this mapping actually takes the upper half z plane to the full complex w plane. Can everybody see that? Is there anyone that this is unclear for? All right. Okay. So great. So now we know about the function w equals z squared. So what about another function? You know, are they all that simple? That was a pretty simple function. Are they all that simple? What about something like z equals w squared? That looks roughly the same, z equals w squared. But actually, it turns out that z equals w squared is significantly different from w equals z squared. This function is what we call a multivalued function. Okay? It's a multivalued function because in order to solve for w as a function of z, I have to take square roots. So I have to write down w is the square root of z. So you've actually already seen this a little bit in your first year calculus, where you take a square root and it's either plus the square root or minus the square root. But the point is that both plus or minus the square root square to the thing that you started off with. Okay, and this is a reflection of the fact that I said on the real line, you can either go left minus or you can go right plus. Okay, things are much more tricky on the complex plane, where I have an infinite number of different ways that things work. So so in this case, it's not a function in the real valued sense that you've learned about. So it doesn't satisfy the vertical line test, but it is a function. It's a multivalued function. However, when we deal with multivalued functions, we have to restrict them to make them single valued so that we can do things with them, like differentiate, integrate, etc. So we're going to be exploring this in much more detail, but let me give you an understanding of where this multivaluedness is coming from. So it turns out that it's easier in this case to work with, instead of Cartesian coordinates, polar coordinates. So let's write z in polar coordinates, so the modulus argument form, right? So we'll write z as r e to the I theta. So r here is the modulus, mod z, and theta is its argument, arg z. Okay. So now if I write z like that, and I know that w is the square root of z, then w is the square root of r times e to the I theta by 2. Yeah, I'll just take the square root of that. Now, what does it mean to be multivalued in this sense? Well, what it means is the following. Suppose I take some point here, right? I'll take this point z0, or let's say z. Yeah, let's call this point z1. Okay, so right up here, so here's a ray r1 theta 1. So z1 here is r1 e to the I theta 1. And then what I'm going to do is I'm going to pick a contour on the complex plane, so some curve on the complex plane. I'm going to throw some words around here. I'll make them more precise a little later when we need them to be more precise. But for now, all you need to know is that this is some curve on a two-dimensional plane, right? You have some intuition for what that means. Your intuition is probably right. So let's traverse these curves. So all of these curves are closed, meaning that they start off and end off at Z1. So here's a red curve, it goes like that. Here's a green curve, it goes like that. Here's a yellow curve, it goes like that. And a purple curve that goes like that. Okay, sorry, the purple curve goes in the other direction. Okay. What I'm going to do to traverse these things is I need to move the ray, right? So the ray just moves and it changes its length. R1 changes as I move along the curve. So to traverse one of these closed curves, I need to add 2 pi to theta. So theta starts off here, theta 1, and then I increase theta and goes like this and it comes back to this. And then when it comes back to the original point, it's theta plus 2 pi. Okay. So as we go along theta to theta plus 2 pi, Z1 comes back to Z1. Great, no problem with that. But what happens to W? Well, W is the square root of Z, right? So W is the square root of R1 e to the I theta over 2. But as theta goes from theta 1 to theta 1 plus 2 pi, this goes to e to the I theta 1 over 2. Fine, no problem with that. But there's another factor of e to the I theta, e to the I pi. But e to the I pi is minus 1. In other words, if I traverse along this red curve, okay, where theta goes from theta to theta plus 2 pi, Z comes back to itself, cool, but W comes back to minus itself. And therein lies the problem. Okay, this is why I said that this function is multivalued. But if I go from theta to theta plus 2 pi, and then go another round around this red curve, so theta plus 4 pi, then I'll pick up a factor of e to the I 2 pi, and e to the I 2 pi is just 1. So in order to return W to its original value, I've got to traverse this curve twice. Okay, so keep that in mind as we go. Is everybody happy with this? Okay. Good. So no objections. I'm going to go on. All right. So I'm just going to go on for 2 more minutes. I don't know whether people are on campus or not on campus, but I'll stop at the definition. I'll stop with this slide, and then we'll pick it up again on Friday. All right. So technically, to encode this stuff that's going on as we do this traversal, we say that this function, W equal to the square root of Z, has 2 branches. Okay. One branch where theta lies between 0 and 2 pi, and another one where theta goes between 2 pi and 4 pi. Right. Here's the key thing, is that on each of these branches, the function W equal to the square root of Z is perfectly single valued. So as long as we stay within one branch, as long as we restrict theta to be within this range or within this range, and I don't care which one for now, these things are dictated by what problem we're trying to solve, but as long as I stay within this range or this range, this function is single valued and I can do stuff with it. I can integrate it, I can differentiate it because it's perfectly single valued within that branch, right? But, and here's the really tricky part, you have to keep the branches separated. And the way we do that is by making what's called a branch cut. So the branch cut in this story is this ray that extends all the way out from 0 to infinity. Okay, it's called a cut line or a branch cut on the complex plane. And what it does is it separates out these branches. So as long as you stay within, as long as you don't cross this line, you're fine. You're staying in your branch. Okay, so on the yellow curve, for example, all right, I make a traversal of a closed curve, but I stay in the one branch. On the green curve, I make a traversal of the green curve, but I stay on that branch. Okay, so as long as you stay inside of the branch, you're fine. The function is well defined. It is single valued. You can do stuff to it. The issue with all of this stuff comes with this point here, the origin, where the square root, the argument of the square root vanishes, right? The argument of the square root, what's sitting inside the square root is just Z. Z vanishes at Z equals 0 at the origin of the complex plane. At the origin of the complex plane is why this function is multivalued. Okay, this point, this special point, is what we call a branch point. Okay, in this case, I have technically 2 branch points. We'll cover why you have 2 branch points a little later, but for now, just know that I have 2 branch points. One is at 0 and one is at infinity. The nice thing about infinity on the complex plane is that while there are technically an infinite number of different ways you can approach to infinity on the complex plane, they're all the same infinity. So I chose the positive real axis to be the branch cut, but I could have chosen the negative real axis. I could have chosen any of the rays, any of the infinite number of rays, and they all get to the same infinity. So there are two branch points in this story. One is at 0, and actually one is at 1 over 0. Okay, so infinity and 0. And the branch cut always connects branch points. So a little later, we'll explore more multivalued functions, like the logarithm function, for example, where the branch points are not just 0 and infinity, but they lie on finite points in the complex plane. And again, we have to restrict our functions, and the way we do that is by drawing a branch cut by cutting the plane between those branch points. Okay? All right. Very good. So very quickly, in fact, let's stop there. That seems like a good place to stop. So we've covered what I wanted to say about functions. On Friday, we will talk about limits and derivatives. Any questions?
Sir?
Yes. Can
you repeat again what makes the origin a branch point? What about it being the origin makes it that?
Okay. So if I go back to this picture here, there are a bunch of different closed curves. Okay. Only one of those closed curves encloses the origin. Can you see that? Can you see it? Only the red curve encloses the origin. The yellow curve goes around, it's a closed curve, but the origin is here and not inside the yellow curve. Similarly for the green curve, similarly for the purple curve. Okay?
Yeah. So what about it? So if the red curve, then it's not a valid path for the multivalued. It won't be a multivalued function. Well, it will be a multivalued function, then it won't be single valued.
No. So forgetting about the multivalued and single valuedness for now, right? The point is that unless I make a branch cut on this thing, this is going to be multivalued. But let's just not worry about the multivaluedness right now. I'm just trying to convey to you what's special about the origin. Okay. What's special about the origin here, even though we're doing algebra on the complex plane, is actually something topological, right? So with a function like the square root of z, the origin is a very special point here because the argument of the function vanishes. So that's why z equals 0. So for example, if I had z minus 1, if I had the square root of z minus 1, then the problematic point would be the point z equals 1. Okay, it's wherever the argument vanishes. Because that point there, any curve that's circling past that point will necessarily pick up these kinds of factors of -1. Any curve that's not circling that point will not.
I mean, so we could draw a closed loop that goes through the positive real axis but doesn't contain the origin. There are no problems in that case. Like it just dips in and out.
Yep, no problems in that case. Because you get equal contributions going on the one side of the complex plane and from the other. You get equal and opposite contributions cutting the complex plane one way and the other way.
Okay. I mean, I don't understand that yet, but
we're going to come back to it a little bit. But if you go to my notes, the picture on the front cover is the geometrical picture of what's going on in the story. That basically what we're doing here is we're taking the complex plane and we're taking multiple copies of the complex plane and we're gluing these copies together in a funky way. So the picture on the front cover is a picture that occurs later in the text where we cut the plane. I don't know if you're looking at it right now. We cut the plane. That's the line that ends at 0 at the origin, and then we glue the one half of the cut to the other half of the cut on another plane, etc. And you can see what's formed there is this kind of spiral staircase of different complex planes. And so when you cross the cut line, what you're doing is you're going from the one complex plane to the other complex plane. That's why it's multivalued. So when what you're doing, Francois, what you're suggesting is to start off with a point, cross into a different what we call sheet or different complex plane, and then cross back again. So there's no problem with that. Again, we'll cover all of this in much more detail a little later when we come to try and understand integration on the complex plane. Okay. Let me stop sharing and turn off the recording.